Okay, so 7172 due. Thank you. And we're going to have an in-class quiz next time.
We get 2 chances still?
So that means no. So that means you can have a 3x5 index card of notes. Okay. Anything in 7172 is what you're probably going to want to look at. Okay. Okay. You guys ready? Yes or yes? Okay, so it's applications of the normal distribution, and we're going to learn how to, as I said, we're going to learn how to use our calculators to get the values. Okay, so the first thing we're going to do is draw a normal curve. And label it with the given mean. We're going to note the value of the standard deviation. Okay. We're going to also label the given bounds. Bound or bounds, depending on how many there are, with an X, with X or X's. And we're going to shade the area of interest. So our first goal here is finding a probability, okay? So maybe we should note that. Finding a normal probability. Okay, step 3, for each X, we're going to find the equivalent Z-score using the Z formula, and then we're going to use our table to actually find the probability. Okay, and then we're going to see how to do all that on the calculator. Once we have it down by hand, and should I close the blinds over there? It's the glare? Okay. Okay, so those are the steps. We're going to be given a normal value, cutoff value. We transfer that over to Z, and then we look up the probability using our table. Okay, let's do problem number 17, the chicken egg one. And for everybody, actually you guys in the online class as well, I'm on page 354. Page 354 in the book. Okay, so it says the mean incubation time of fertilized chicken eggs kept at 100.5 degrees Fahrenheit in a still air incubator is 21 days. Suppose that the incubation times are approximately normally distributed, and as we discussed last week, approximately normally distributed, they're actually one and the same. So the variable here is the incubation time. We use restaurant notation for chicken there. Okay, these eggs have a mean incubation time of 21 days, standard deviation of 1 day. Okay, in part A, we want the probability that a randomly selected fertilized chicken egg hatches in less than 20 days. Okay, so remember that area and probability are one and the same. Okay, they're one and the same. So we've got a mean here of 21 days, and we want the probability that the hatching time of a chicken egg is less than 20 days. So this becomes your cutoff value. Okay, find it with relationship to the mean. Okay? And remember, this is all about X, the distribution of the hatching times for the chicken eggs. You guys with me? Okay, good? Okay, so 20, as long as your cutoff values are in correct proximity to the mean and to each other, you'll be fine. Okay? So we know that 20 is less than the mean, and the probability that the hatching time is less than 21 days would be represented by the area to the left of that cutoff value. You guys are with me? Less than that way, more than that way, right? Like just like a number line. Okay. Crud, we need another. Oh, there's a chair over there. There's a chair over there, Quincy. Okay, so now to find this on our calculator, we need to translate it over to Z, right? Because as you recall, our table is in terms of Z. All right, so we're going to translate that over. And my advice to you is to write all your X and Z values below, your probabilities or areas or percentages or whatever above, to keep stuff straight, because we're going to turn around and do this entire process backwards. Okay? So we take this cutoff value that is now an X, we're going to convert it over to a Z using the Z-score formula. So Z equals X minus mu divided by sigma. In our case, the X is the cutoff value, the 20. The mu is the mean, 21. And divided by the current standard deviation, which is 1. Which is also the standard deviation of standard normal distribution, right? Just so happens that standard deviations are the same. That doesn't happen very often, but. Okay, so we get what? -1? Is that right? Okay. Okay, so our equivalent Z value to that X value is -1. And in the land of standard normal, recall that the mean is 0. Okay. So now we want that area to the left, and when we look up that Z-score of -1.00 on our table, it gives us the area to which side? To the left, good. So we'll actually, just by looking up this Z value, we'll get the area that we want. Okay, so looking up that Z-score of -1.00, so we go to the side of our Z table that has negative Z-scores, we look up -1.00, and we get what? 0.1587? Do you guys get that? Okay. So what's the probability that a chicken egg hatches in less than 20 days? 0.1587, good. So what percentage of chicken eggs hatch in less than 20 days? What percentage of chicken eggs? Good, 15.87% of chicken eggs hatch in 20 days or less. You with me? And remember that for a continuous distribution, whether or not you include the cutoff value is irrelevant. So our answer, 0.1587, and we're good to go. Okay. Now, because I've got just a small board space, I want to go through some of these problems, and then we'll come back and make sure that we are all solid on this, and then we'll come back and do it by calculator, okay? Does that sound all right? Plan? It's a plan. Okay, so part B says, what's the probability that a randomly selected fertilized chicken egg takes over 22 days to hatch? Okay. So this part stays the same. We're still on the chicken egg problem. And now in part B, we want the probability that a hatching time is more than 22 days. Okay? Make sense? Okay? So again, you've got, and X is normally distributed. You might add that in. Okay? So when X is normally distributed, you have your normal curve. You set up your mean, 21 days. And you're looking for, so your cutoff is the 22 days. The value that you're looking for, I guess like a demarcation line between the piece of probability that you want and that you don't want is at 22 days. Okay? So 22 days is bigger than the mean, so it'll go over here somewhere. And the X's beyond 22 days are going to be on the right-hand side. So next step is what?
Z-score.
Sorry?
Z-score.
Good, z-score, convert. Okay, so remember, this is all about X. Before we can look up the probability that we want, we have to convert over to Z. So let's do that. So at Z, the mean is 0. And that corresponding X value, right? And as I discussed last week, X and Z are just like different units, okay? They're like miles and kilometers. You're just converting. You're converting. Okay, so you're going to take your cutoff value, subtract the mean, divide by the standard deviation, and it looks like that's positive 1, right? 1.00, is that right? But now when we look that up on our table, which we're now ready to do, when we look this value up on our table, it gives us which area? To the left, because that's the way the table works. Okay, so we look up that 1, and we get all of this area to the left of the area we want, which is what? What do we get?
0.84.
0.8.
Wait, we want the positive one?
Yeah.
That's 0.8413.
0.8413. Does everyone agree? Thank you, Scott. 0.8413. Okay. So remember, the z-score in your table always gives you the area to the left. So now if we have the area to the left, but we want the area to the right, what do we do? 1 minus, perfect. So to find the area that we're seeking, we do a 1 minus 0.8413, which gives us what? I'm sorry? 0.1587, Kevin? Isn't that what we got last time?
Yep.
Because those are symmetric values, right? Does that make sense to you? Okay?
But we could have just done the -1, right? Like we wanted to.
Right, right, absolutely. So you can look up -1 as well. You get the piece of probability that we got last time, and then you would just think about it flipped over to the other side. So remember, your z-scores can be negative, but your probability cannot. Okay, it's an area. Yeah, so the value of 20 in part A is 1 standard deviation below the mean. Okay? The value of 22 in part B is 1 standard deviation above the mean. So it should make sense that the probability pieces out on those ends are symmetric. Does it? Okay. Okay. 1 standard deviation away on either side. Okay. Okay, we're going to do part C, and then we'll look at the calculator. Okay, because part C is going to be the easiest to do in your calculator. Okay, so what's the probability that a randomly selected fertilized chicken egg hatches in between 19 and 21 days? This would be important stuff if you were a chicken farmer, right? I mean, you got to know when to be around, get ready to take care of little baby chickens. Okay, what's the probability that our chicken egg hatches between 19 and 21 days? So Normally distributed, set up your curve, stick in your mean. 21's at the mean, right? So that's our, one of our, say, cutoff values or X values. And then 19 is going to be below that, say down here somewhere. And we want the area in the middle corresponds to the probability. Okay. Yeah? Does that make sense? Good. Okay, so remember this is in X. Now we convert over to Z. What's the Z-score for the mean? What's the mean in the Z distribution? Sorry?
Z-score is 0.
The Z-mean is 0. Yeah, the Z-mean is 0. So that's the equivalent Z-score for a mean of 21. Okay, the mean in Z is always 0. Okay? And then we'll want to Z the X value of 19. So we'll do that by, and remember to, if you're not getting the correct Z-score, you got to either group the numerator with parens, or you have to do this in 2 steps. Okay? So we've got X, which is 19, subtract the mean, divide by the standard deviation, which is 1. What do we get? Do we get negative 2? Okay. Okay, so what do we know here about the probability? Oh, that's where you were going, huh, Brian?
Yeah.
Yeah. What do we know about the probability at 0? 0.5. Yeah. Okay. So the probability all the way up to the mean, right? You got half on each side. Total always 1, half on each side. So the probability, we don't have to look that one up, yeah? Probability is 0.5000. And then what is the probability when we look up negative 2?
0.0228.
0.0228?
Yeah.
So then, remember that when we look up the probability, or we write the probability for the mean, it gives us all of the area to the left. We only want to this line. So we're going to find the area below and then subtract it off. So the probability that we're seeking is 0.5000 minus 0.0228. And what do we get there?
0.4772.
0.4772? Thank you, Mike. Everyone agree? Everyone good with that? Cool. Lauren?
How do you quantify the
Total area under any probability curve is 1. Okay? And because the distribution is symmetric, it's like a mirror image of each other across the mean. And we're going up to just the mean. So we automatically know the probability there is half. Okay? I added the zeros because I knew that the value we look up in the table was going to come out with 4 decimal places. Okay, so the probability that our chicken egg hatches between 19 and 21 days is 0.4772. Or another way you could look at it is the percentage of fertilized chicken eggs that hatch between 19 and 21 days, 47.72%. You with me? Okay, good. Are you ready to try this on calculator?
Yes.
So when you do this on calculator, you don't have to convert to Z. The calculator is going to do that for you, and you don't have to look up the probability using the table. The calculator is going to do that for you too. Okay? It's kind of rocking. All right, let's give it a shot. Okay, so there's my calculator screen. We're going to use that distribution menu, and remember that there's a normal probability handout on my website. I was very proud. One of my colleagues emailed me over the weekend and said that his daughter is taking a stat class at Sac State or something, and she was having trouble with the TI functions, and he referred her to my website, and she thought it was great, gave her everything she needed to know. So I hope you guys use that too. I can't help it, you know. I spend a lot of time on those. It helps that they're useful. Okay, so we're going to go into that distribution menu. We hit second VARs. Second VARs, and that takes us into the distribution menu, and this is where we found the probability, the binomial probability distribution, right? So anyway, use the handouts. They're useful. You're going to go down to normal CDF. The continuous functions work a little bit different than the discrete ones. Okay, remember with the binomial there were two different functions that we could use to find probabilities, but they just work differently. Okay, with the normal, if you want to graph a normal curve, and you'll see this on the handout, you'll use normal PDF. But if you want to find a probability, you automatically go normal CDF. Okay? So you drag that to your home screen, and now what the function wants in those parens is it wants the lower bound of the chunk of probability you're seeking, comma, upper bound, comma, mean and standard deviation. Okay? So the lower bound would be the 19. So again, you don't have to worry about any of this. You don't have to worry about any of that. Okay, the calculator's going to do it all for you. So you go lower bound 19, comma, upper bound 21? Yeah, 21, comma, mean is 21, standard deviation 1, and there you go, 0.4772. Now, the calculator is a lot more accurate than the table because the table is, all the values are rounded. So you might get, you might be off a few, like, you know, out in the 4th decimal place, but it should be fine with MyMathLab because they set you, what do I want to say, a margin of error for your answer that's big enough to accommodate that difference. Kevin?
Why did you put 21 in twice?
Sorry?
You put 21 in twice?
Lower bound, upper bound, that's these guys. And then the mean, so you have to repeat it in this case, and the standard deviation. Now, if you were in Z, okay, let's say that we already transferred this over to Z. Was that -2? That was -2.
They wouldn't call like X1 and X2.
Sorry?
They wouldn't call it X1 and X2 versus lower bound and upper
That's
bound.
just, you could, if you want to, you know, put it in your head as like X1, X2, that's great. It's just kind of what I call it. Lower bound always being the furthest left-hand bound of the chunk you're seeking. Upper bound is always like the largest boundary. Okay, so it's kind of reading it left to right. Let's say that you already had converted this to Z. When you use normal CDF in Z, you only have to put the lower bound and the upper bound. The mean and the standard deviation is implied. So you would go -2, and you don't have to put the 0.00, up to 0, and then just enter. So if you do not put in a mean and standard deviation, the calculator will assume that you are in Z, or standard normal. Does that make sense? You guys with me there? Okay. Okay, so let's go back to maybe parts A and B. In part A, we had the probability that it was less than 20 days, that the hatching time was less than 20 days. Okay, this gets a little funky because you got to think about it. Now the distribution here goes to negative infinity. Okay? The tail never meets the x-axis or never crosses it. It just snuggles up closer, 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 closer to it until the two are almost indistinguishable from each other. And that doesn't happen, it doesn't take very long for that to happen, right? We know that 99.7% of the areas they're only after 3 standard deviations, right? So it does that really quick, but still, there's no like set boundary on the left-hand side or right-hand side in the extremes. Does that make sense? So you just have to kind of go, okay, when I'm setting a left-hand boundary here, I just have to put in a really small value. With respect to 20, I've got a standard deviation of 1. Heck, we could just put in 0. Right? So, overestimating the extreme left-hand boundary in this case is advisable. Okay, you want to make sure that your significant number of standard deviations, if you put 5, even if you put 10, that would be fine. You're not going to see a difference with respect to your decimal places. You with me? Does that make sense? You guys with me? You're all just kind of not really sure about that. Tell me, how do you feel about this? Okay, does it make sense? Okay, good. Okay, yeah, give me a thumbs up or a thumb sideways or a thumbs down. Okay, thank you. I appreciate that. Okay, so a few people are still confused. Okay, so this distribution does not have a set beginning and end. So if we're finding a probability to the left of some value, this thing technically just keeps sinking on down to the x-axis, gets closer, 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 closer. But again, within 4 standard deviations or so, you're not going to see the difference between the axis and the curve. So what you need to do is just put something. Okay, the calculator needs a left-hand bound. You got to give it something. Okay, so for your left-hand bound here, let's write LHB. And the x of 20 would be your right-hand bound in the calculator, or lower bound, or x1, or an upper bound, or x2, however you choose to call it. You with me? Okay? So when you need to set a number for your left-hand bound, you just have to make sure that you're going to pick up a sufficient amount of probability to 4 decimal places. So you know your mean is 21, your standard deviation is 1. So actually, if you did the mean minus 4 standard deviations, that would suffice. Okay? But, you know, if you want to just make it easy on yourself, just go really small. 0 or... You know what does that make sense? 10, I don't think you're going to see a difference if you put 0 or if you put 10. Somebody try 10, I'll try 0, and we'll see. And then your right-hand bound is going to be the 20. Mean 21, standard deviation 1. And what did we get last time? Same? 0.1587? Was it just the same or is it a little bit different? 0.1587 last time? Okay, cool. Then it's just the same.
They rounded up on the sheet.
Okay. So again, my math lab is going to give you, or my stat lab is going to give you enough wiggle room for these little bitty differences. And you know, these are only tens, hundreds, thousands. These are only in the 10,000ths. That would only be 1/10,000th difference. It's not, you know, it's not going to make your answer that much different. Very negotiable. Okay, you with me? Is that all right? Let's go back to, go ahead, Scott.
I'm confused why we do this versus not just putting like the lower bound, all the givens they give us.
Okay, if we want this chunk of area or probability, and we want to use the calculator, it needs a lower bound to be specified. So we have to figure out something that represents that lower or extreme left-hand bound to tell it. So did somebody else put a 10 here? Did it work are you the same to 9 decimal places? Yeah. So what you have to just make sure is you want to make sure that you've captured all the significant probability in the lower edge of the distribution. Let's try it again with going the other direction, okay? What was part B?
Greater than.
Thank you. Probability that the hatching time was greater than 22?
Yes.
Okay, so we want that area. So we have a similar problem as the last piece, part A, except now we've got to put in we have to make up an upper bound or a right-hand bound. You guys with me? Or an X2, or however you want to look at it. Okay. So now you want to take the mean and add sufficiently many, say 4 standard deviations. 4 standard deviations will do it easy. So if you go 21, 22, 23, 25, if you go up to, say 25 for an upper bound, you'll be fine. Okay, and again, how did I get here? I took the mean and added 4 standard deviations. That's not a very good mu. If you add or subtract 4 standard deviations from the mean to get your lower or your upper boundary, you'll be good to go. So in the calculator, that means second vars 2, okay? Lower bound is now the 22. The upper bound is 25, comma, comma, mean, standard deviation, yeah, 0.1586. What we got last time? 0.1586? Some people prefer to do these problems by hand, and that's fine. It doesn't take you all that much more time, and if you understand them better, then go for it, absolutely. Let's try another one together, shall we?
We're just like kind of converting it into like a between problem.
Sorry? Yeah, exactly. We're setting some kind of an upper end so that we can make it a like between problem, between this value and that value, how much probability. Exactly. Okay, there we go. Fast food restaurants spend quite a bit of time studying the amount of time cars spend in their drive-thrus. People want to get their stuff and go, right? That's the point. They want to be fast. That's why they call it fast food, I'll bet. Certainly, the faster the cars get through the drive-thru, the more the opportunity for making money. Well, that too, right? You get to service more people. In 2007, QSR magazine studied drive-thru times for fast food restaurants, and Wendy's had the best time with a mean time spent in the drive-thru of 138.5 seconds. Wow. Assuming drive-thru times are normally distributed with a standard deviation of 29 seconds, answer the following. Okay. So now our variable is the time in a Wendy's drive-thru. Mean is 138.5. Standard deviation is 19 seconds? No, 29, yeah? 29 seconds, okay. And those are in seconds, and part A, we want the probability that a randomly selected car will get through Wendy's in less than 100 seconds. So we want the probability that the time spent in the drive-through is less than 100 seconds. Okay, is the notation and that stuff okay with you guys? You with me there? Okay. So this is a normally distributed variable. You've got a mean time of 138.5. Okay, so 100 is going to be below that somewhere. Do you want to, yeah, let's do it by hand too. Next step would be, remember these are x's. We want to convert those over to z's. The mean is 100. We want to take this cutoff value, convert it to a z-score. Take the cutoff, subtract the mean, divide by the standard deviation. What do we get?
Negative 1.32.
Negative 1.32? Anyone agree? Negative 1.32? 3.3?
Oh, yeah.
Okay. So write this stuff down, on exam 3. Draw me a little sketch or write out what you put in your calculator so I know what you did. Even if you can like see it in your mind's eye and you just pound it out on the calculator, at least write out what you put in your calculator in case you make a little tiny error. Okay? So that value of 100 seconds is 1.33 standard deviations below the mean. And if we look up that z-score, it's going to give us our probability of interest, which is what? What do we get?
0.0918.
0.0918. Everyone agree? Okay, so you're going to spend less than 100 seconds in a Wendy's drive-through a little over 9% of the time. Okay? So let's go on to part B. What's the probability that a randomly selected car will spend more than 160 seconds? Oh, we ought to do this by calculator, huh? Let's do that. Okay, so we're going to get the normal CDF. We need a lower bound. How about 0?
Yeah.
Easy. Upper bound, 100. Mean. Is that right? Yeah. Standard deviation, 0.9212. Yeah, to 4 decimal places, 0.0922. But again, those little differences, not significant. And in my stat lab, if you have any issues at all with it not taking your rounded value, let me know. Or your calculator value, because it should be fine. Should be fine. Okay, let's tackle part B. And it's not unusual for students to just feel more comfortable doing these by hand. That happens frequently. So if the by hand method just works better for you, don't worry about it. I always on a, you know, test to me, like, you know, exam 3, I always do the problems both ways. And either method is perfectly fine. Okay, what's the probability that a car will spend more than 160 seconds? Okay. Mean of 138.5. Boy, I can't draw a mu today. Okay, 160 is on the upper end. Down here somewhere. And we want the probability out in that extreme value. So the calculator, we're going to need to create an upper bound. For the by hand method, remember that this is x. We're going to convert all that over to z with a mean of 0. And the corresponding z-score there. Take your x, subtract the mean, divide by the standard deviation. Am I going too fast? You guys okay? Okay. Online students, you'll still have a online quiz this week, of course. That's my. But maybe, you know what I'll do is after you guys have your quiz, I'll post it for the online students and just to let them know what we did. I can use it for study. What do we get? Huh?
The Z,
Yeah.
0.74.
0.74? Thank you. Everyone agree? 0.74? So when we look up the 0.74, it's going to give us the area to the left, which is, everybody got it?
.7704.
0.7704. Everyone agree? Even if you're all about using the calculator at this point, keep practicing by hand too, because we're going to reverse this whole process. And it can be really confusing. Do I have a probability? Do I have a z? Do I have an x? Which piece do I have and which piece do I need? Okay, so keep practicing. And so what's our probability of interest? We're going to do a 1 minus 0.7704. What do we get there?
0.2296.
What's that, Mark?
0.2296.
0.2296? Thank you. 0.2296. So about 23% of the time, you're going to spend 160 seconds or more in the Wendy's drive-thru. Anybody use the Wendy's drive-thru? Is it fast? Is it fast?
I did it yesterday.
You did it yesterday. Was it fast?
Really fast.
Is it fast? Yeah? Okay, they're saying they're the fastest. Okay. Calculator, let's try that. Second, VARS 2. Lower bound 160. What do you want to use for an upper bound there? What do you think?
4,000.
Yeah, you could use something ridiculously big if you want. Yeah, 10,000.
Yeah, 'cause
But actually at about, I think maybe at 200, it isn't going to be big enough. I would go, let's just go 500. You know, just something you want to make sure that you're at least, say if you round up and make the standard deviation 30, okay? 30 times 4 times 4 is 120, right? So you want to make sure that you've got this plus about 120. So 300 should actually be fine, but yeah, something easy. Then your mean, 138.5, and your standard deviation of 29.2292. So again, a few decimal places off, but it's insignificant. Okay. How are you guys feeling about this? Good? You all right, Lauren?
When you said like you put in the lower bound and upper bound first on the calculator,
Mm-hmm.
didn't you say that the left's the lower bound?
Yeah, the left-hand side is always going to be what goes in first. The left-hand cutoff value of the area you're looking at, and then the right-hand part goes in second.
Oh, okay, so 160 is the cutoff.
Yeah,
of the left.
yeah, right. Left-hand bound, or lower bound, right-hand bound, or upper bound. Okay. Let's go backwards. We didn't do this but that's fine. Because I want to make sure and get all this stuff in today. So let's say you have, you're given a probability, and you want to go backwards and find the x that results in that probability. So we're going to do the entire process backwards. Okay, so steps to find a data value corresponding to a percentage, percentile, or probability. You're going to draw the normal curve. Of interest and label it with the given mean. And note the value of the standard deviation. You're going to shade the area of known probability. And determine the location or locations, depending if you're looking for one or two numbers, of your unknown x's. So we're going to refer to the refer to the standard normal table backwards, like we did last time, looking up a probability and finding a z to find the z-score of interest or scores. And then we're going to find, or let's put it this way. Convert the z's, z or z's, to x or x's using which is the z formula solved for x. Okay? So we use the table, right? We look up, we find the z-score and we look for the corresponding probability. To go backwards, we look at the probability and then backwards look at the corresponding z-value. To use the z formula backwards, okay, because the whole process is backwards, you've got your z formula, right? You're going to solve for x, right? You did this in algebra, solving for a variable, right? Multiply both sides by mu to clear the denominator, so you have z sigma, those cancel, equals x minus mu. Add mu to both sides and you're good to go. You with me? Okay. Add mu, cancel, and you have x, I'm going to bring that over here, equals z sigma plus mu. And it takes you from a z-score back to an x. Make sense? Okay? Just kind of wanted to show you how that is. You don't have to do that every time. The formula, you can just use it. Okay? What do you think? You ready?
Let's have a new title.
Same section. Same. So this is finding the data value corresponding to a percentage or a probability as opposed to finding the probability. Okay. Let's go back to our chicken egg problem. This is number 25, next page. Okay, so here we go. We're on number 25. It says the mean incubation time of fertilized chicken eggs kept at 100.5 degrees Fahrenheit in a still air incubator is 21 days. Suppose that the incubation times are approximately normally distributed with a standard deviation of 1 day. Okay, so now they want us to determine the 17th percentile for incubation times of fertilized chicken eggs. Recall that a percentile is just smaller pieces of like quartiles, right? So at the first quartile, you know that 25% of the data is at or below, 75% is at or above. Okay? Here at the 17th percentile, 17% at or below, 83% at or above. You with me? Okay, does that make sense? So, again, our variable is a fertilized chicken egg. It's normally distributed. Mean 21 days, standard deviation of a day. Okay, so part A. We want the 17th percentile. So what that means is, okay, here's our mean of 21 days. What that means is we want the x value that determines the time or the number of days when 17% of the eggs hatch less than that time, 83% hatch more than that time. So on what side of the distribution is the 17th percentile, and how do we know? Anybody? How do we know? Where is it? Is it over here? The 17th percentile? No? How come? How much of the data is at or below the 17th percentile? How much data is at or below? 17%. Okay. How much data is under this whole curve? What's the percentage? 100%. Okay, good. How much is here at the mean? How much is on each side? 50-50? Okay, so if I want 17% to the left, it's going to be down here somewhere. You with me? Does that make sense? Okay. And that's what we're looking for. Yeah, Kevin?
Why would it only be from one side?
Sorry?
Why would it only be from one side? The area.
Why would it, say again?
It's like, it says you want the 17th percentile, but you're only getting the 17% from one side of the graph.
Oh, because of the definition of a percentile. 17% of the data is at or below. So 17%, let me rephrase. So if 17% of the data is at or below the 17th percentile, that means 17% of the area under the curve is also at or below that cutoff value. You with me?
You're saying it goes in numerical order to a sense, so you can't cut off that way and say it's 17% on the right side.
Yeah, if you did it over here, that would be the 83rd percentile. You with me? Because the whatever percentile is that much data below, at or below, by definition. Okay? So, this is our goal. Okay, and just for the record, we've got 0.83 over the rest of the distribution. Okay, so our first step, I think you're going to especially like the calculator for this part. The first step is we've got our probability. We look this up in our table and go backwards and find the corresponding z-score. So you're going to grab your table. And remember, you're on the left-hand side, so you want to go on the side with negative z-scores. And you're going to look in the middle of the table because we have a probability. And we're going to find the closest thing we can to 0.17. And .1700. So I see a .1711. Do you guys see it? And then the next smaller is a .1685. So the .1685 is .0015 too little, and the .1711 is only .0011 too big. So it's closer. Do you agree? Okay. What's that corresponding z-score? Negative 0.95. Do you agree? Negative 0.95. So first step, you use the table backwards, okay, to find the z-score. And then second step, you take the z-score, plug it into the reverse z formula to get back to what that x is. So we've got x equals z sigma plus mu. So take the z-score. Note the positive or negative. It's really important. Multiply it by the standard deviation and add the mean. So all the pieces you need will be there. They'll be given. But you can agree, this is, you got to keep straight what you have and what you need. Like here, you got to remember that you've got a probability, you're looking for a z. So you look in the middle of the table, not on the edge. Okay? What do we get? $20.05? So 17% of the chicken eggs are going to hatch before 20.05 days. You guys with me? Okay, calculator. So the inverse norm command is the reverse process. So you're going to take inverse norm to your home screen. And in the argument, it wants the percent of probability to the left, just like the table would work. Okay, always to the left of that cutoff value you're seeking. And if you have one over here, you have this thing, chopped up, you may need to add all of your pieces of probability to the left. but it has to be the total probability to the left of whatever value you're seeking. Does that make sense? Okay. So it would be 0.17, mean, standard deviation, done. There's your 20.05. And here you usually come out right on the money. Once in a while, you know, a 100th off or so, but yeah, Lauren.
So you're doing the same thing as you put the lower one and the upper one too?
No, not here. You just want the bound, since the bound is what you're seeking, you want all the probability below it. Okay? Let's go back. Let's go back to the problem. Let's look at part B. We want to determine the incubation times that make up the middle 95% of fertilized chicken eggs. The X's, we're going to get 2 of them. And notice it says middle 95%. So we've got our normal curve. And middle 95% means there would be equivalent area on each end, right? Which is, what, 0.025? Is that right? Subtract from 1, cut in half. So we want this X and also this one. I'll call them X1 and X2 to keep them separate. Is that all right? Okay. So X1, look up the probability to the left, find the z-score. Oh, we might want to, you guys have that? So you're looking at 0.025, you know it's negative on your z table. So if you find 0.025, ooh, it's exact. Do you see it? Negative 1.96. Do you agree? Do you see it? You guys with me? Let me know if you're having issues. Okay, because remember that you're looking up an area, not a z-score. You're going backward to find the z, so you're looking in here for the 0.025. Negative 1.96. Okay, and then we're going to run this thing through the backwards z formula to find the corresponding x. So x1 equals z1 times sigma plus mu. So negative 1.96 times the standard deviation of 1 plus the mean of 21. And what do we get there? So in a couple of days, this video will be posted on my online website. If you guys want to go back and go over this, you can. Feel free. It's for you too. 19.04. Okay, so that's this value. So 2.5% of the chicken eggs hatch in about 19 days or less. So let's find our other x. And in the book, they'll probably just call it 19 days. So what do we know about this z-score? I think that's where you were going, huh, Mike?
Yeah.
Yeah. So what is this z-score over here?
The same.
It's positive 1.96. How come?
Symmetric.
Symmetry? Okay, symmetry. So it's the positive version. My equal sign isn't very good there. Okay, so we've already done that. Now, if, no, I'll leave that for a minute. Okay, so going backwards from Z2 to X2, let's see, I'll put that up here. X2 equals Z2 sigma plus mu. And that isn't times 2, that's the second Z-score, the second X value. Okay, so Z2 is this guy, positive 1.96, multiplied by 1, add the mean, and what do we get? What'd you get, Courtney? 23.96? 22.96, thank you. Anyone agree? Disagree? Cool. So there's our other X value. So 95% of these chicken eggs hatch between 19.04 and 22.96 days. You with me? Okay, cool. And that would be the middle 95%. Okay, so doing this on the calculator real quick before we head out. Okay, so if we were looking for X1, okay, second VAERS, you want inverse norm, probability to the left, 0.025, mean, 21 days, standard deviation, 1 day, 19.04. You guys with me? Now when you find Z or X2, when you find X2, you've got to add up all the probability to the left. So you're going to have to add these two pieces together because they're both to the left of that score we're seeking. You with me? So you got to add the 0.95 and the 0.025. So what would that be? 0.975? Again, because you want all the probability to the left of your value that you're looking for. Mean of 21, standard deviation of 1, and there's our 22.96. Okay, you with me? Boy, that took 30 seconds. Huh? So again, it's up to you which method you want to use. If you use one and you can't get the right answer, you might try the other one. Send me questions if you have them. Bring them to class next time. And remember, you can always go back and refer to the videos and review the problems. Thank you.